In general and organic chemistry, hybridization is often introduced after chemical bonding and molecular geometry, and for good reason. We need to understand bonding and geometry before taking a deeper dive into explaining bonding in molecules. Take carbon, for example. Here is the electron diagram for the ground state of carbon. It has 6 electrons. But for bonding purposes, only the valence electrons can participate in bonds. So let's ignore the core electrons in the 1s orbital. Carbon has 4 valence electrons. Recall, these are electrons in the outermost principal quantum number, 2 in this case. Here is methane, CH4, the simplest hydrocarbon. In methane, carbon participates in 4 single bonds with 4 hydrogen atoms. Let's take a closer look at these bonds. Each bond is a shared pair of electrons, with one electron from the carbon and the other from the hydrogen. These are called covalent bonds. Covalent meaning atoms sharing a valence electron. But look at carbon a little closer. In order for these 4 single bonds to exist, there must be 4 unpaired valence electrons for carbon. Each unpaired electron can then bond to 4 hydrogen atoms. But in the electron diagram, there are a pair of electrons in the 1s orbital and 2 unpaired electrons in 2 of the 3 p orbitals. Let's be clear. The diagram is for the ground state non-bonding carbon atom. But now we are studying carbon atoms that are bonding. Thus, this diagram wouldn't apply. This is hybridization theory. Hybridization is a mix of the valence atomic orbitals to form new orbitals for bonding. Imagine if all 4 valence orbitals mix, 1 s orbital and 3 p orbitals. The result are 4 hybrid orbitals, all degenerate, which means equal in energy. Notice, the energy of these bonding orbitals is somewhere in between the energy of unhybridized s and p orbitals. And following Hund's rule, we can maximize unpaired electrons. There are 4 unpaired electrons. We can call these 4 orbitals sp3 hybridized orbitals. We can say that sp3 orbitals have 25% s orbital character. Recall, s orbitals are spherical shaped. And they have 75% p orbital character. Recall, p orbitals are dumbbell shaped. And there are 3 p orbitals along the x, y, and z axes. I'm showing only one p orbital here. Therefore, the hybridized orbital would have about 75% dumbbell shape and about 25% spherical shape. You can think of them as balloon or teardrop shaped. In this example, we can call carbon sp3 hybridized. Hybridization also governs molecular geometry, along with the concept of Vesper theory. These hybrid orbitals take up space. The best shape for these 4 balloons to be in are in a tetrahedral geometry. In our methane example, we see 4 covalent bonds, or shared pairs of electrons. A shared pair of electrons in a hybrid orbital is called a sigma bond. We can say that methane has 4 sigma bonds. Let's go back to our diagram. Not all four orbitals have to mix. In some cases, only three orbitals mix. The lowest energy s orbital can mix with only two of the three p orbitals. This will result in three hybrid orbitals. These are called sp2 orbitals. In this case, notice there is one unhybridized p orbital. Following Hund's rule, there are still four unpaired electrons for carbon, three in each of the hybridized orbitals, and one in the unhybridized p orbital. We saw for sp3 hybridization, there was a 25% s orbital character and 75% p orbital character. In sp2 orbitals, there is a 1/3 or 33% s orbital character and 2/3 or 67% p orbital character. There is more of the lower energy s orbital character in the sp2 orbitals. We can say this carbon atom is sp2 hybridized. These three hybrid orbitals take up space. Thus, their geometry is optimum in a trigonal planar geometry. Here, we are looking at a view from above, or a bird's eye view. Let's rotate the figure to have a side view. Here is the side view with the three electrons, and I included a red plane for perspective. Recall, there is an unhybridized p orbital, which is dumbbell-shaped. And the best position for this p orbital is perpendicular to the plane. Let's move the one electron into the p orbital. And we'll move it over for a brief moment. Now, this is important. What happens when another sp2 hybridized atom is nearby? We'll use another sp2 carbon in this example. Let's focus on the middle. Our first carbon atom is sp2 hybridized. This sp2 hybridized orbital can overlap and form a covalent bond with the sp2 hybridized orbital of the second sp2 hybridized carbon. This bond between the hybridized orbitals is called the sigma bond. Now, let's bring the unhybridized p orbitals back. Notice, above the plane, there is another pair of electrons. These unhybridized p orbitals can overlap to form another bond. This shared pair forms a second bond between the carbon atoms and is called a pi bond. Let's discuss the bond energies. The sigma bond is between the lower energy sp2 orbitals, thus a strong bond, about 347 kilojoules per mole. The pi bond forms from the higher energy unhybridized p orbitals, thus a weaker bond, about 264 kilojoules per mole. This plays a role in the reactivity of the pi bond, or pi electrons, in organic chemistry reactions. The pi electrons are more reactive than the sigma electrons. The two bonds between the carbon atoms can be called a double bond. When seeing these two lines between carbon atoms, students often ask me which is the sigma bond and which is the pi bond. My response is it doesn't matter. Just understand that one of these lines is the sigma bond, which is the lower energy sp2 hybrid orbital overlap, and the stronger bond. And one of the lines is the pi bond, which is from the higher energy p unhybridized orbital overlap and a weaker bond. Next, hybridization can also occur with only two orbitals. Here, one s and one p orbital can mix to form two sp orbitals. This leaves two unhybridized p orbitals. For sp orbitals, 50% is s orbital character and 50% is p orbital character. These two orbitals maximize their distance, thus exhibit a linear geometry. Interestingly, there are two unhybridized p orbitals. Here is one p orbital. I'll remove the hybridized orbitals from view so we can see the second p orbital clearer. The second p orbital is oriented perpendicular to the other p orbital and the two linear hybridized orbitals. You can imagine this p orbital pointing into and out of your screen. I'll bring back the hybridized orbitals and add the unpaired electron to each of the unhybridized p orbitals. Let's remove the p orbitals for a clearer view. We can say this carbon atom is sp hybridized. Now, what if another sp hybridized carbon is nearby? There is an overlap of the sp orbitals and an overlap of the unhybridized p orbitals. The overlap of the sp orbitals forms one sigma bond. And the overlap of the unhybridized p orbitals forms two pi bonds. The other hybridized orbitals can form sigma bonds to other atoms. Here I'll show the simple example with hydrogen atoms. The three bonds between carbon atoms can be called a triple bond. Third row and larger elements have d orbitals available for mixing. Let's go back to the diagram and bring these d orbitals into view. When the s orbital and three p orbitals mix with one d orbital, these five hybrid orbitals are called dsp3 orbitals. When an s orbital and three p orbitals mix with two d orbitals, these six hybrid orbitals are called d2sp3 orbitals. Now, let's recap. Hybridized orbitals is mixing of the atomic orbitals to create new orbitals for bonding. In organic chemistry, we often see second row elements carbon, nitrogen, and oxygen. Only s and p orbitals can hybridize for these elements. Hydrogen has only one 1s orbital, thus no hybridization occurs for hydrogen. sp3 hybrid orbitals are four degenerate orbitals in a tetrahedral geometry. sp2 hybrid orbitals are three degenerate orbitals in a trigonal planar geometry. sp hybrid orbitals are two degenerate orbitals in a linear geometry. dsp3 hybrid orbitals are five degenerate orbitals with a trigonal bipyramid geometry. And d2sp3 hybrid orbitals are six degenerate orbitals with an octahedral geometry. Let's close with a few exercises. Here are the general rules. Count electron pairs around a central atom. These include a sigma bond or sigma electron pair and a lone pair of electrons. These electron pairs will occupy a hybrid orbital. We'll call these electron pairs groups. Groups are sigma bonds and lone pairs. Here's an easier way to think of counting. Since each atom around a central atom must be bonded by at least one sigma bond, we can think of groups as simply atoms and lone pairs of electrons around a central atom. Here's the general table. Notice each group requires a hybrid orbital. The electron pair geometries tell the geometries of the hybrid orbitals. The molecular geometries are not shown here and are dependent on the number of sigma bonds and lone pairs of electrons around a central atom. I'll refer you to my other videos on molecular geometries. Let's practice finding hybridization here. So let's start with our first example. Here's an organic molecule. It contains a chain of carbon atoms here, and then at the end we have this OH group. This is the alcohol functional group. Let's go ahead and find these hybridizations for these non-hydrogen atoms. I'll start from left to right. So we'll start with this carbon atom right here. And we want to count the groups. Now there's two ways to think about this. The first way is just to count sigma bonds and lone pairs. So around this carbon, we see these four single bonds. And remember, every connection to an atom is going to contain at least one sigma bond. And so here's 1, 2, 3, 4 sigma bonds and 0 lone pairs. The other way you can think about this is just count the atom. Since every atom must have one sigma bond, you're looking at 1, 2, 3, 4 atoms that are bonded to this central carbon. And so we'll call this 4 groups. And here's the last part here. The 4 groups, those 4 sigma bonds or sigma electrons, will occupy a hybrid orbital. So in order to have 4 groups, we must have 4 hybrid orbitals. So this would be an sp3 hybridized carbon. Let's go to this carbon next. This carbon has a triple bond or is participating in a triple bond, and then there's a single bond here. So let's count these bonds. Here's a sigma bond. And in the triple bond, as we talked about, one will always be a sigma bond. And there's 2 extra bonds. So remember, these groups, these atoms, are always bonded by at least one sigma bond. Anything extra will be a pi. So in this case, there's 1 sigma bond and 2 pi's. So in terms of groups, this carbon atom has 2 sigma bonds, no lone pairs, and so we'll call this 2 groups. And to have 2 groups, you have to have 2 hybrid orbitals, and so this carbon is sp hybridized. Take a look at this carbon atom, and you'll probably notice something very similar. This carbon atom is participating in the same triple bond as our previous carbon atom, and this carbon atom also has one other atom on the other side. So this carbon atom looks a lot like this carbon atom. So again, 2 sigma bonds and no lone pairs. This is 2 groups. And so we'll call this carbon sp hybridized. To our next carbon, one of the things you'll notice, this carbon has 4 sigma bonds. We can also count the atoms, 1, 2, 3, 4 atoms, no lone pairs. So this carbon atom looks a lot like our first carbon atom. 4 groups, we'll call that sp3 hybridized. And finally, here at the end, let's look at this oxygen atom. This oxygen has 2 sigma bonds, or we can call this 2 atoms around it. That's 2 groups. Notice, a little bit different than the other carbons, this oxygen atom has 2 lone pairs. So lone pairs count as groups too. Those lone pairs will occupy a hybrid orbital. So interesting here, we have 4 groups. The 4 groups are 2 bonds or 2 sigma bonds and 2 lone pairs. For these other carbon atoms, the 4 groups were 4 sigma bonds. So a little bit different, but still 4 groups. So this oxygen is sp3 hybridized. Here's our second example. I'll go from left to right. Here's a carbon atom with 4 atoms around it. We'll call that 4 groups. Four sigma bonds. And so that's sp3 hybridized. The second carbon, it's surrounded by 1, 2, 3 atoms or 3 groups. There's no lone pairs of electrons. There's a sigma bond between the carbon atom, and anything extra will be a pi. So there's a pi bond there too. But there are 3 sigma bonds and no lone pairs. We're going to count that as 3 groups. And so 3 groups have to occupy hybrid orbitals. So we need 3 hybrid orbitals. This carbon is sp2. Let's go up to the oxygen next. So oxygen also participating in this double bond. It has 1 atom around it, the carbon atom, and 2 lone pairs. So we'll count that as 3 groups. So this oxygen is also sp2 hybridized. We'll look at the next carbon atom. This carbon atom has 3 atoms around it and no lone pairs. We'll call that 3 groups. This carbon is sp2. And here at the end, here's a nitrogen. It has 2 atoms around it. Those atoms are connected by sigma bonds, so we'll call that 2 groups. It also has 1 lone pair, and so this is 3 groups. And so we'll call this sp2. Each group must have a hybrid orbital. In chemistry, especially organic chemistry, we'll see groups of atoms. So instead of drawing the individual bonds here, we'll just draw this, what's called a condensed formula. And so we'll just group the CH3 together, and we'll show the 1 bond to the central carbon atom. So when you're looking at this right here, what this really means is that we have these hydrogens that are bonded to the carbon atom. And so at this point, you should realize that when you see these groups, these 3 hydrogens are single bonded to that carbon. So you see 3 hydrogens, you'll have 3 single bonds or sigma bonds, and then here's a 4th sigma bond. So pretty common here, 4 groups, sp3. And what do you recognize here? Well, this is the exact same thing, sp3. And then right here, sp3. So I did this intentionally. We're looking at something new here. Here's a carbon with a positive charge. So I have other videos on formal charges, and I'll refer you to that. In this case, carbon with a positive charge only has 3 bonds and no lone pairs. So interestingly, this is 3 groups, And so this carbon with a positive charge is sp2 hybridized. This is something we'll definitely see in organic chemistry. These are called carbocations. And very important for substitution and elimination reactions. And here's an example for inorganic chemistry or general chemistry students. I just wanted to throw this last example in here. Let's look at the central atom only. This is a PCl5, phosphorus pentachloride. Pretty common in inorganic chemistry and general chemistry. These third row elements are bigger, can accommodate extra electrons. In this case, here's a phosphorus that has 5 sigma bonds. So around the phosphorus, you're looking at 10 valence electrons, which violates the octet rule, but it's okay for these third row or bigger elements. So in this case, this is interesting. We have 5 groups, and 5 groups have to occupy those hybrid orbitals. You always start with the lower energy orbitals first. So here's 4 hybrid orbitals, sp3, but we need a 5th orbital, and that 5th orbital will come from those d orbitals. So 1 d orbital, 1 s orbital, and 3 p orbitals will hybridize. This is called dsp3. We'll close with this example. Xenon tetrafluoride, pretty common in inorganic chemistry and general chemistry. The xenon in this case can form these 4 sigma bonds to the fluorine atoms, but also has the 2 lone pairs of electrons, so this will count as 6 groups total. So here are 4 hybrid orbitals, sp3, and we need 2 more, and those 2 will come from those extra d orbitals.